photo I found. We are getting there. Okay. So, thank you so much. So yeah, before I start, I would like to thank Ivy and Vicente for like the amazing things these guys do. So yeah. Model computation. So how many of you know this word? Have seen it in news or somewhere? Okay, that's fine. How many of you know this guy? Okay, so nobody knows this guy? Okay, so this is the guy who made the neural nets work. Okay, so the all AI revolution is because of him. So he's Hinton. Okay, so he's the guy who invented backpropagation. He invented the LXNet in 2012. He invented capsules. Now he invented GLOM, the Boltzmann machine, and before that, when people gave up on neural nets in 1980s, this guy was still working on that. So one of the oldest people, he got it during, I think, last 2 years ago. So there is a reason I am showing his photograph. Because he came up with this paper called How to Represent Part-All Hierarchies in a Neural Network. It's a philosophical paper, okay? It came in 2021, and this paper was not describing a working system. So it was just like something he said, published it, but it was not working. So a lot of people in the community didn't like it, and it was quickly hijacked by the people who wanted some more concrete results. So that's why he never ended up publishing this paper in a big place, just put it upon archive. So that's the whole thing.
You should explain what archive is.
Okay, archive is a server where you put in all your papers, whatever research you do. So it's a preprint server. It need not be published, but you can put all the cool stuff you do there so that people across the world can see it. So it's hosted by Cornell. Now, who am I? So last time I gave a talk here to around one year ago. So this is the timeline. So in May 21, Hinton came out with his cool paper, GLOM. And in September, I started my PhD at CRCV. I tried to get this idea working. Most people didn't believe in it and still don't. And I spent 1 year banging my head on it, nothing happened. Then in 23 of January, Hinton published this forward paper, very popular paper. Nothing happened again. Still I failed. Then in August, I had a success. Somewhat I got it to work, and then we got a paper in NeurIPS in 23. So it does not work fully, but it is still good enough that I can give a talk on it. And I didn't achieve any state of the art, but what I am presenting is some alternate system which can start acting as an alternative to transformers. Not exactly transformers, but yeah, I think that's the thing. So now a lot of people ask me, what do you do? So I just say that I try to make neural networks detect objects. So you give them images and try to find where the objects are in the scene. That's all I do. So I don't do any cool stuff. Okay, so it's just a basic question my research evolves around. So what do you expect? Like just setting the expectations before I proceed. So what I will talk about is mostly philosophical stuff, which has become a scientific reality now. And if you have more technical questions, you can always go and read the paper. But the purpose of this talk is to give you the bigger ideas, which you don't find in any paper, any talk, or any book. Okay? So I guarantee you that much. So I will say very weird things, and most of you will not agree with it, okay? It will be nonsense. So you will all say it's impossible, whatever I'm going to say. And I will also jump too much. You will find me talking somewhere here, somewhere there, and you will say these are just weird connections. But all I am saying is just stay with me, and hopefully by the end, you will see some connections, okay? So, how people have done AI since last 10 years. So you have a big GPU, and you have a model, right? So what do? You take a giant model, we call it a transformer, okay? And what you do is that You take a even fat GPU, right? Then you put this model on the GPU, so that big fat guy is on the GPU, and then you give it data, give it a lot of data, then you train it, and you say that it has become intelligent, right? That's how we do the AI. Any AI model, if you pick right now, that's how we do it. So, man, why is it? What happened? Okay, but so if you have some hard problem, let's say you want to do object detection, what you do is you say, okay, I want to do some problem, I want the AI to solve some problem, I'll give it data, I'll give it some labels, I will train it some more, and I have solved it, right? I just gather the data for the shit I want, I pump it through the transformer, run my GPUs for some day or some months, and I have this big fat model which works, right? And we say that transformers are God, so they are Thanos. Okay, cool. So everyone is with me, right? This is how we do AI. Anyone doesn't agree? Okay, cool. So now my argument, what I am saying is that neural networks can't do three things, okay? No matter how much data you give them, no matter how much memory you give them, and the maximum GPU we have right now is 80 gig amperes, right? And you don't have any GPU greater than 80 gigs. So even if you put like one batch size on the machine and put it on a single GPU, that's the maximum limit, the 80 gig thing. And there is a new GPU NVIDIA came up with. So this 80 gig memory is the maximum limit to what you can do. And the other thing I am saying is that people say that intelligence is equal to number of neurons which your network has. So for example, if you look at ChatGPT, it has around 100 billion neurons, and humans have only 86 billion neurons in their brain. So you can see that the count of the neurons in the GPT has already surpassed that of humans. So if the intelligence was just the count of neurons, GPT should have become smarter than us, but I don't think it has. Okay, it's good, but it's not great. So it seems that the answer is not about scaling up in terms of number of neurons, but there are still some things the machines can't do. And you can't just scale them up because GPT has already surpassed human performance in terms of human neuron numbers, but it still doesn't work. So there are three problems I will say which neural nets can't do. So the first one is something I call object collapse problem. So I have a question for you guys. How many objects do you see in this image? One, okay. Does anyone have any other answer other than one? Okay, it's one, right? Cool. How many objects do you see here?
It's not determinable.
Why?
Because there are presumably many leaves in the background, but to distinguish between how many leaves there are implicitly in a discrete sense would be impossible given my visual acuity.
Wouldn't it just be
Right.
But it's inferentiable that there are a large number of leaves, branches, and twigs in the background,
Got it.
as
So-
well as particles of water in the clouds.
Got it. So you understand what I'm saying, right? So everyone got what he said? So the number of objects in this are indeterminate. There are many, right? Okay, cool. So most of people would say that I have a giraffe, I have some tree, and I have some shit called background, because what he said, the visual acuity is too less to care about it. Okay? So that is what most of us would expect. So the detector will genuinely detect only three objects, like the giraffe, the background cloud maybe, and the tree. But like what you said, that this thing has infinite number of objects. So you have giraffe, the spots on the giraffe, the hair of the giraffe. So each individual hair, I can see that, right? I can see that, it's within my visual acuity. But no detector can detect it.
It depends on what you define an object to be. You could go down to molecules, you could go down to
Yes.
atoms, you could go down to constituents of atoms. It depends
Yes.
on where you draw the boundaries.
Right, but when you talk about the perceptual space, here you are not able to see finer than the hair, right? I agree with you what you're saying. So the question is that if there are an infinite number of objects in this scene, can we detect all the objects? And the definition of object is somewhat ambiguous, right? So object detection is not as easy as we think it is. Okay, so another question I have. Can you count the leaves in this?
Give you enough time, okay?
Can you count the leaves in this area?
We'll try. Good.
Cool. So, well, there are 200-ish leaves. I can count, but you need the time to count them, right? You can count them. It's not impossible because I can say, okay, 1 leaf, 2 leaf, 3 leaf, 4 leaf, 5 leaf, 6 leaf, right? So you can count the leaf here, but it takes time to you for counting it, right? But given enough time, you can count it. Everyone agrees? Okay. But here is how a neural network will do this task. So you take a transformer and you take these queries, and each query will say that I will give the segmentation mask of one of the leaves. Okay? So if you have 200 leaves here, you will feed in 200 queries here. Okay? If you have 300 leaves there, you will feed 300 queries there. Okay? So this is the parameters you learn for the model, and each color represents one leaf.
So how will you explain a query like intuitively?
Hold that question. Okay? We'll come back to that.
Okay.
So each query here can be thought of as something which specializes an object. So for example, this leaf, this red thing corresponds to an object, one leaf. Okay, so if there are 200 leaves there, you need 200 of these, right? That's how all the transformers of the world have worked. So in case you have 4 leaves, you need 4 of these queries. So the problem arises here. So if you have 200 leaves to be decoded, you require 200 queries, and each query occupies additional memory. So let's say each of these query occupies, let's say, when you feed the shit through the transformer, it occupies, let's say, 500 MB. Okay? Now I told you that our maximum GPU is like 80 gigs. So maximum, if each one occupies 500 MB, you can decode 160 objects, right? But this image has more than 160 objects, 160 leaves. Now your brain was able to count it, it took more time. This network doesn't take more time because it's a transformer, it does whole thing in parallel, but its memory explodes. And that's the problem in all the models out there right now. That if you increase the number of objects too much in the scene, then you run out of the memory. And no matter how well you build it, you will have this problem. So, are you able to understand what I'm trying to say? Okay, cool. So, your brain never went out of memory, right? It took more time. So here is the problem. Your brain could solve it, it took more time. Transformers didn't take much time, but they went out of memory. So there is something wrong going on in transformers. Okay? Computer vision, I talked to a lot of computer vision guys. And when I talked to them, they just laughed at me. So they told me that we don't care about this. And surprisingly, some of these were the inventors of RCNN, fast RCNN, and faster RCNN, all these big models. So they just laughed. I was like, okay, that's fine. So they said that in this you only have 3 objects, and you detect these 3, and people don't care about finer granularities, right? But if you don't, that doesn't mean other doesn't, right? You can't change the fundamental thing. So if you care about reality, then the models we have right now won't work.
So why don't they care about anything more than the highest level of abstraction as far as what can be considered?
Because when you are a company and you want to sell some product, you will build a self-driving car and you just care about the objects, you don't care about the thing. You just care about whether you hit a person, you don't care about whether you hit his head.
So they only care about the highest abstraction.
Right, because it sells their business.
Of an object.
Right.
So anything that is the least discernible from the rest.
Right.
And I feel like that's more of like from precedent, like some of the initial models, like
Right.
data.
Right.
Yeah.
So we will break some models, don't worry. Now, surprisingly, there are neural nets which can do this. They can encode this infinite world, no matter how many objects in constant number of parameters. So I took a simple perceptron, only 85,000 neurons, and I encoded the whole L3 Harris building in this. So this is one model with 85,000 neurons encoding all the trees and their leaves, even the tiles here. You can see the resolution. You see each tile. And this network has only 85,000 neurons, and it can encode the whole scene no matter the number of objects in it in a constant amount of memory. So 85,000 neurons only. But the shit we call transformers has a 5 million parameters and they can't do this. Okay? So this much we have done. I am showing you a working system. Okay? So you agree that neural nets can do this, but transformers can't. Okay, and a dumb perceptron, simple perceptron can do this. Simple perceptron, nothing more. Just linear layers stacked together. Okay, cool. So now there is second problem, which I call perceptual crowding problem. Here is another question. So this is an image having 3 by 3 dimension. It has 9 pixels. How many objects can this have? How many objects do you think, maximum objects this image can have?
10, 11, 12, 13.
Means you can have one object per pixel, right? Other than that, the
Or if
object
you
will
have to
go
make
out of the
the
view of the
pixel.
camera, right? So if you put an apple in each of these slots, you have one object in each of the slot, right? You agree? Okay. So in CNN, the convolutional kernel is 3 by 3, 5 by 5. It's not even 1 by 1. So it cannot detect such small objects. But theoretically, in this thing, you can have 9 objects with 1 object per pixel. You agree? You agree? Am I correct?
No, 9 per pixel.
No, so 1 object per pixel.
Okay, yeah.
So do you agree? Is this correct?
You can't have an object occupy more than one person.
You could, but I'm asking maximum objects.
Okay.
So can we go greater than 9? Really? Okay. So here I have shown you 10 objects. Agree? So in the same 9 pixels, you can pack 10 objects also. Now, here is the funny question. Can a neural network detect a peer? There we go. Why? Because if you think about segmentation, at every pixel we are solving a multi-class problem. We are asking, at this pixel what object is there? Is it an apple or is it a pear? But at this pixel, apple and pear both are there, right? But when you do segmentation on this, applying a softmax, it will fail. Because the softmax only allows one object to go high and all other objects to go low. Got it? So segmentation will fail. All the models. So neural networks cannot segment multiple instances corresponding to the same pixel, although your brains can. Now, I don't agree with this thing. I don't agree with Hinton on this. So if you see here, in his capsules paper, Hinton assumed that there is only one instance of the entity at a location. So this is the assumption he made like 2 years ago, and this is the same assumption everyone has been following since the last 10 years. But in this problem, although it's a relevant task, we are not able to solve it. It's very funny, right? Okay, how many of you know this paper? One of the classiest papers. Segment anything. Okay, so we call this model to be very nice. So ICCV, this was, I think ICCV happened last week? Last week, right?
I think so, yeah.
Yeah, ICCV happened last week, so these guys got the best paper award. Best paper honorable mention. But here is what it can't do. So if you look at the decoder takes a point. So let's say I have that same giraffe and I mark that point. Okay, so what they will output as the segmentation is maybe some segmentation containing the spot and some segmentation containing the whole giraffe, okay? Now, the question I ask you is, what is correct? The spot or the giraffe? You don't know, right? Both are correct. Or should it make this relationship that this is the giraffe at the root and this is the spot at the node? Something which you call as a dynamic parts tree. A parts tree which connects the object with the body parts in a tree fashion.
Ideally, yeah, but
So it cannot form these dynamic parse trees, and neither can it tell you that if it at this point it segmented many things out, what are the most relevant, right? So it can segment body parts and the objects, but it cannot form these dynamic parse trees. Okay? Cool. So everyone is with me? I hope it's not too technical. Okay. So SAM can segment parts, but it cannot establish relationship between them. So if you look at the problems, there are 3 problems out of which one has been solved by segment anything, because when I took that point on the giraffe, I got the spot as well as the whole giraffe. So for the same pixel, it decoded more 2 objects, right? So it solved that crowding problem, but it cannot solve these 2 problems.
What if we had more control over how our brains organize synaptic architecture? Would we be able to take less time without this limitation simultaneously?
Right. Yes.
You think so?
Yes.
What's the other?
So my question is, can you solve these red problems in the same network? That's the key thing. So here is the big idea which Hinton had 2 years ago. So when a human is born, you start from something called a zygote, and then you copy this zygote and you form a baby, right? This is how biology works. Similarly, you plant a seed, it becomes a plant, right? So can you do this something similar for a neural network? Like you start with, so if you have 2 babies, if you have 2 children and both of them belong to the same family, same genetics, and so how many, have you seen that Foundation TV series on Apple? No, okay. So you know how clones are formed, right? You take the same DNA, no mutation, copy it, 2 people you form are identical. So is it possible to do this with neural networks? So can you start from a single embedding, a single cell, copy it many times and have it form a neural network? If you could, what can it do? That's the key question he asked. Because we already make the neural nets big and then train them, but he asked a basic question, that whatever a human is in a single cell. If you can manage to encode that single information in a DNA, that's all you need. If you can understand what a human is, that information is in a single DNA. By just copying that DNA, you can form a human. You don't need to form the whole neural network on the computer. So on a 2-dimensional grid, I had this nice video. So on a 2-dimensional grid, the intelligence already exists. So this is a convex game of life. So you have like these square cells in which each of the cell has a state, whether it's alive or dead. And then each cell will interact with 8 neighbors. Okay, so you have a grid, each cell interacts with 8 neighbors. And there are some rules that if you have some live neighbors, less live neighbors around you, you become dead. And if you have 2 or 3 live neighbors, you move on to the next generation. And if you have overcrowding, you die. So if there are too many cells around you, you die. Only these 3 simple rules, and this is what you obtain. So this is the movement. This is a glider gun. So this pattern just emerges with those rules. There is nothing. There is no other learning happening here. Just those 2 rules you encoded. So you have a grid in which you have a cell, and that cell has just those 3 rules, and that's just a 2D grid. And these patterns can emerge. So can we do better? You start with a single cell, but instead of making it 2-dimensional, make it more dimensional. That's what Hinton said. So here is how you make it in vision. That you take an image, it has a cat in it, you take this embedding, and this embedding is like a very large network, a large number of numbers, and a very large vector. Now what you do is, you copy this embedding across the locations. Like the DNA of a child gets copied. So what you do is that you start with this single cell, this single embedding, and then you copy it across the image locations, okay? So this is the step when you copy this embedding and you copy it across all the locations. This is the step I call unfolding. Then you get a neural network in which you have these columns, right? Each pixel gets copied, each embedding gets copied. So you have these towers, right? Towers, 1 cross 1. Now you perform, using that tower, you perform some intelligent task, let's say classification, backprop, okay? And now compress whole embedding into one. And repeat this step for all the images in the batch. So the idea is this, that a single cell is not intelligent, it is dumb. Because if I just take a seed, it's not a plant, but it already has the DNA. So when you copy it, you form a neural network, and now that neural network can learn because enough copies form the thing, right? Now, once you have learned, you backprop, adjust the weights, and you collapse the whole network back into a single embedding you started with. And now, when you copy this embedding many times, you end up with something I call a machine brain, because it's a brain. It's a single neuron copied many times, which gives you a brain. Now that brain learns through backprop, and then you unfold it, the whole knowledge back into the cell's DNA, and you copy it again. So the idea is, whatever learning you do, you copy it and unfold it. So next time, so already you know a bit of the DNA structure, and as you keep copying it, the next time you copy it, it will be better. And automatically it will form the whole human. So this is the big idea. Now, coming to that objects thing, here is how it will function. So at your body, the lowest level, every cell has a nucleus. So the lowest level indicates the lowest level of the objects, the pixel level. Then some pixels form objects. For example, some cells group in your body to form liver, and some cells form the brain. And then at the highest level, maybe the upper arm, lower arm forms the whole arm, some things form the arm, and some things form the torso. And then as you go up, the whole thing forms the human. So if you look at this at the lowest level, the number of cells are very much high, because there can be liver cell, any cell, right? As you go up, these cells start clustering themselves, and the number of objects you detect become less. So at the topmost level, you have only one human. But when you go down, maybe some of the cells will start forming a head. So these similar arrows means that they belong to the head, and these similar arrows means that they belong to the nose, or they belong to the leg. Now this same head at the lower level can be broken down maybe into 2 vectors. So these 2 represent the nose, and this represents the lip.
Rajat?
Yeah.
So just like from my understanding, like with the giraffe image, if we were to look at it again with this model, if you looked at the pixel of the spot, it would grow basically, and then it would be like that's a spot
Right.
on the second level,
Right.
and then it would eventually form so that each spot next to each other makes the giraffe.
Right, so giraffe is like this 2D image, right? And when you copy this, this becomes like pillars on it.
Okay.
Each of the pillar is an embedding, and this embedding has different levels. So you can think of it as a 1 cross 1 convolution.
Okay.
So did you get this, what I'm trying to say? Everyone got it? Okay, so at the lowest level, you have the cells. At the biggest level, you have the organs. Then at the next level, you have body parts, and then you have the whole human. Okay? So you do this for every pixel. Okay? So now, This sounds very good idea. The key challenge was getting it to work. It sounds cool, it's biologically plausible. So the question is that the idea is cool, but does it work? The answer was barely. So so one of my friends, Nicola, in CVPR 22, he published this paper called agglomerator. So what he does is that this is the pixel, you start a single embedding, copy it, and as you grow it, you can see these nice islands emerging, you see? So here, these similar colors means that they belong to the same object. So in my previous figure, I had this arrow, right? So let me go back. So I had these arrows, right? So if 3 arrows agree, it means that they belong to the same object. So in this image, similar colors mean that they belong to the same object. So here, all these orangish colors are meaning that they belong to the aeroplane, and this dark color means that they belong to the background. Okay? So they got this to work. Now, so you understood this? Like how I copied one embedding and how the similar colors in this map mean that they belong to the same object. Really? Okay, you seem flustered.
I'm just thinking.
Okay. Yeah, so basically the method is, they followed is do whatever Hinton said. Okay, just do it. And hope to God it works. Okay? And just train this whole shit on classification. You don't need to tell it this is the exact location where this aeroplane was present. You don't need to supervise it. And hopefully these islands emerge, which you can see emerging. So by just training this network for classification, they were able to do that. And the results were pathetic. Okay? So out of 5 data sets, only 1 data set they had state of the art. So this is the error rate, small error rate means better. So only on 1 data set they had better rates. On all others they were performing very bad. You see? And this was CVPR 2022. So it's a published paper.
What's S-Node data set?
Small node.
Small node.
You're right.
What is it about? Like, what does it have?
It just has black and white images of 3D objects. Now, this paper only showed results on 1 out of 5 data sets, and it was an oral at CVPR. Okay, so it means there are still people who do good research and are not caring about results because they made this concept of islands work. That objects which belong to the pixels which belong to the same objects automatically group together when you copy this embedding. Okay.
So why is this a priority of significance above the results?
Because the significance is that you are operating at a pixel level. So when you operate at a pixel level, you can't go finer than that. So ideally, by making these islands form,
So it's
you are
operating
encoding
defined
all
as
the
level of
objects.
distinguishment like we were talking earlier.
Right.
Okay.
So this was only working on synthetic. Okay, so this is CVPR 2022, last year, July. Get the timeline, okay? Cool. So I came after attending CVPR and I was like, okay, wow, I will do some cutting edge work now. And I thought, okay, let me steal their model and make it work for videos, and I failed. So the state of the art classification accuracy is 99, I was getting a bare 12%. So then I thought, what's wrong? What's going wrong? So I thought that I need to break this problem into smaller parts. The first part is, can you make these islands emerge in real images? Can you copy a single embedding and have it do intelligent stuff? And can you dynamically grow networks on a hardware? So if you solve these 3 problems step by step, you could combine all these and form this system which I'm talking about. Okay? Everyone is with me, or no, it's becoming too boring? It's becoming boring, right? Okay, so you understood all these 3 questions. What's the first question about? What do you mean by first question? Can you make islands emerge in real images?
As in like real life images? Or-
Right.
Yeah, yeah.
So the islands I showed you, that aeroplane, that was on a fake image, right? Not a real image that much. And can you copy the single embedding and have it do intelligent stuff like detection, or perception or tracking. So I'm not talking smaller problems, I'm talking some of the biggest problems in vision. The third one is, can you grow this network on hardware, right? So once achieved, you could call this whole system as GLOM. So can you make islands emerge in real images? That was the first question, right? So this is what we did in our paper, in our ULIPS paper now. So we were able to show that you can get these islands in real images. How? I don't do anything actually. I didn't do anything, and that's the funny thing. So I take the transformer, pump in some video through it, and just look at the outputs of the transformer. That's all. I don't do anything. I just pass this through the transformer and train this whole network on classification. Okay? I'm not doing anything. So I am not training this network using any type of instance supervision. I'm never telling it where the actor is, or where this TV is, or where this cat is. I am not telling it at all. There is no annotation. And there is no distillation, no contrastive loss, nothing, only classification loss. Okay? Now, the only different thing I am doing is that I am performing TSNE on the output tokens. So you guys know what TSNE is? Okay, just imagine it's some mamba jamba, okay? It does something, but what does it do? This is what it does. So without any label, you can see that the girls' pixels gave themselves their own color and they grouped themselves. You see? And similarly, I can find individual water bottles forming their own clusters. And this is without any supervision. Okay? And this is the first layer of the transformer, not even sixth layer. So neural networks are made of many layers, right? We do this in the first layer. This is not even the 10th layer.
So for the original picture, I see that it's like colored blue for some objects. Is that in order to make the islands appear better?
This one?
Yeah. On the
Oh
left.
yeah, that is my problem because when I visualized it, I put the blue map first. I should have done it RGB, I did it BGR.
Oh, okay.
OpenCV has an issue, like it reads in BGR. So this is the strongest point. First layer of the neural net can cluster objects together, perform instance level supervision, like perform instance level separation and form these islands without any supervision. That's the selling point. And here if you see, I can detect all the objects. Like people would say I just care about this guy, but if you look at this shed, we can see these partitions emerging. You see? Now, we can break objects into parts. So see this cow? It's got broken. So we break the objects into parts without supervision, nothing. So this floor, it's not even legible that much, but it can get segmented when you do this type of clustering. So this is the funny thing, that we didn't do anything and we still ended up with it. So it was literally a chance discovery. So one of the biggest problems in computer vision is to detect circular edges. So you can see how it gets the bike, right? Then there is some dreaming ability. There is no window here, but you can see things if there is a window. So there is some deep dreaming going on. And this is where we were 10 years ago. So when convolutional nets came in 2012, people showed that the deeper layers of the convolutional nets encode objects. So at the third layer of convolutional nets, if you see here, if you give it a car, you can see this bare miserable car emerging, right? 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 After 10 years, this is what we are showing now. So we are, right.
Are you going to go into the tendency or like the mechanism behind the selection for like for, because, yeah, there's something here that I'm not quite understanding, like the baseline of the emergent property, I guess.
Right, there is no baseline, that's the beauty. I just pumped it through transformer, took the outputs, and performed TSNE clustering on the tokens. That's all. So this is just simple clustering, nothing else. There is nothing fancy here. The surprising thing is nobody did it for 10 years. That's the surprise thing. So we are the first to show that in the first layer of transformers itself, without any supervision, these objects can emerge. And you can see why this is a big deal, at least for me, because this is where we were 10 years ago. This paper has 30,000 citations now. Okay, so the thing we achieved now has a deeper meaning because you can make these islands emerge. Okay, good. So everyone is with me. Okay, so now this is my second question, right? Can copying single embedding do intelligent things? Right? When the child copies itself, the DNA, the child's brain gets formed, right? So can the whole shit do anything intelligent? Can we do that? So yeah, I banged my head on this for 2 years, and then I come up with something I started calling collapsing positional fields. It's a fancy name, but yeah. So to give it a context, I sent an email to Hinton. He said, okay, it's cool. So what is this about? So I told you this limitation, right? That if you have object queries, so each object was decoding a leaf. So if this transformer was trained on 100 queries, it would only decode 100 objects. If you give it an image with 200 objects, it can't decode it. It has to retrain itself. Okay? Now, so the problem is that the transformer was detecting 100 objects, and if your image had 200 objects, you had to retrain the whole shit. Okay? Now you could always argue that I could train it with 1000 objects, but I could always put 12,000 objects on it. So there is no upper limit to that problem, okay? But there is a maximum limit on which you can train, because then the memory of the GPU will blow up. That 500 MB example I took, okay? So now you had to retrain this thing. So now here is the big thing. So see all the detectors. So RCNN used 20,000 proposals, right? So if your image had 100 objects, you used 20,000 proposals in RCNN. Fast RCNN used 20,000 proposals. Faster RCNN used 300 proposals, and DETR used 100 proposals. So COCO has objects, 100 objects in the image. They thought that, okay, every object can have 100 proposals, so one query for each object. And since I have 100 objects, this is the maximum objects I can go. Like for decoding 100 objects, I need 100 proposals, right? This is what we think, right? So this is the assumption limit. So our common sense suggests we can't go below this, right? And that's the reason that this paper came out in 2020, and since then you never see the number of queries going down. Okay? Now, here is what I am saying. So, I can do it with 1. I don't even need 100. I can decode it with 1. Okay, how? So what you do is you start with a single embedding, which is like the child DNA, copy it, attach a label to it. It is position 1, position 2, position 3. Pump it through a nerve, pump it through self-attention, cross-attentions, and you have 3 detections. So when you're doing a forward pass, if you have to detect 1000 objects, copy this thing 1000 times. Got it? Pump it through the transformer, detect it. Go back, collapse this whole shit into 1. Simple idea, right? Embarrassingly simple idea.
You gotta explain like more like the intuition behind like all those things. You're like there's a many technical terms right there. Linear,
Okay, so
keys and values.
So cross attention, self attention, and queries. This is already transformer. All I did was start from single embedding and copy it many times. That's all. There is nothing else.
I remember you once explained me what was the intuition behind using a single embedding, but like the human intuition behind that.
Right.
Wow.
Because the humans start from a single zygote, single DNA.
Uh-huh.
So you want the decoding to start from a single embedding. Now if you want to decode 1,000 objects, copy it 1,000 times.
So you have this cell that begins like general cell and then it specializes in
Right.
different.
Right. Now if I just use E, if I remove these labels, all the inputs to the network are same. Right? If I only use E. So I cannot decode unique objects with it, right? If I decode you all are different people. I can't give same input to the network to have different outputs. So to break that symmetry, I needed to apply this label 1, 2, 3. But the label 1, 2, 3 is non-parametric because I just attach a one hard-coded integer to it. That's all. So 1, 2, 3 here is a positional embedding used in 1D positional embedding. Okay, cool. That's all I did. So here is what happens. So when I take the DNA and copy it twice, in this image I can detect one person. Then I copy 3 times, 15 times, 30 times, 40 times, 50 times. So the number of queries in the transformers can become dynamic. And to decode dynamic number of objects, you don't need to retrain the transformer anymore. So this is the core idea. And you can see it's not by chance. We are able to decode actual objects. You don't see these boxes lying scattered here. They are actually giving you objects. So it is doing something intelligible.
So those of the over there at which things start appearing have like any meaning. Like you need to like, oh, give me like one object. The first object that pops up, is it more important that if you ask like, give me 5, like they have 5 queries. Is it more like those 5 are like the 5 most
No,
objects?
it can give you any 5 objects.
No, but the question is like, is there any pattern? Like,
No.
no?
No, the reason is because transformers apply attention. Attention is a parallel operation. So they say that we have 5 doors, anyone can enter our door.
Mm.
So they don't make a queue. Okay, so it's an unordered set problem. Objects are coming out of it, there is no order.
Uh-huh.
So
Were you encoding with some order at the beginning? When you had the
Mhm.
embeddings, you were encoding them with position 1, position 2, position
Right.
3, right?
yes. Now the funny thing is that using this single embedding, we were able to do detection and segmentation, classification, and I have gotten it working on tracking. So I can do video object tracking also.
Just like a general observation, this seems like it's just training but before the creation of the model, right?
No, it's creating it along with the model, because when the model forward passes are created, so if you go back, the training loop, so if your batch has, let's say, 20 objects, like if you sample a batch of 4 images and any image has maximum 20 objects, you copy the embeddings 20 times and you decode it. Got it? Did that answer your question?
Yeah, I think so, yeah.
So if your batch has maximum 20 objects, you don't need to copy the embedding 100 times. Just copy 20 times. It will train your transformer faster. Right? Okay, cool. So yeah, this is the last slide. So what's next? So I have been able to get this single embedding working. So the problem is, how do I unfold this in a better way? Because right now I am just copying it and attaching this 1D label, 1, 2, 3, 4, right? But the unfolding happens in some fancier way, which can be learned, which I am not learning. And one way is like, if you see the DeepMind's protein unfolding problem, the AlphaGo system, it automatically does that. It starts from amino acids and predicts the structure of the whole protein. So in our case, the amino acid is equivalent to the embedding and protein structure is equivalent to some perception problem, right? You just have to make the relations and steal from there and apply it. That's all. And the other thing is, how do you learn networks which grow on hardware? So you need to get rid of backprop and instead use forward. Yeah, I am doing some of this, but I don't have anything to show for it. Yeah, that's all. Okay, cool. So any questions you have? Yeah.
If I were to get into the technical nitty-gritty of how GLOM works specifically, what kind of research paper should I?
There is only one paper, and that's the beauty, right? There is no line of research.
Is it that new? Yeah.
Yeah. Let's see. This is the paper.
Okay, so that's the title.
Right. So you can see the power of this. One embedding getting copied does everything, and how it can be beneficial for transformers. Like, because you encoded all knowledge, so you don't need to do distillation anymore. Because let's say you have a stronger hardware, a weaker hardware, you make a stronger teacher model, a very big model, let's say ChatGPT, compress whole shit into one embedding. Now on your cell phone, just copy that shit smaller number of times. Now when you copy it smaller number of times, it will have the entire knowledge, but it will be weaker as compared to the ChatGPT which existed on a 80 gig GPU. But you don't need to train a separate model because you compressed all the big ChatGPT into one embedding. So this is the appeal, that if you manage to compress the whole knowledge in one embedding, just copying it smaller number of times will result in a weaker hardware, and that will achieve implicit distillation. You don't need to do any distillation. So that will get rid of all this gradient matching and things like that. But that's just like hypothesis, but I think we can get there in like next, I don't know. It's tough to say. Yeah, but we'll get there. Cool. Any other questions? Okay.
You discussed protein folding as a relational problem, correct?
Approaching what?
For the AlphaGo solution to protein folding, you said that you discussed it as a relational problem.
Right.
Okay.
So you understood, right? When you are unfolding.
Yeah, we studied it in one of my bioinformatics classes, and I was interested in hearing more about how AlphaGo went about the solution to protein folding.
Right. So I looked at their paper, and it's very much engineered right now. It's not elegant. So I tried to bring in some fancy things. I tried them, nothing worked. So the surprising thing is, all like the most technical, complicated things I tried never worked. And the simplest, dumbest things worked. So I don't know, like, I am still stumped on that. Right. Okay, then, hail Hinton.
Thank you.
Hi, this is John.
Thank you so much.